In a prior video, we have examined a Carnot cycle with the purpose of demonstrating that the change in entropy in a cycle is zero, and that means that the entropy is a state function. In this video, we delve a little deeper into these Carnot heat engine cycles to talk about the efficiency of a heat engine. Okay, so let's try to do here a thermodynamic analysis of energy transfer in this Carnot cycle. Remember that you have 4 steps. You have a reversible isothermal expansion of a gas, then an adiabatic reversible expansion of the gas, then of course that arrow points the other way. Then you have reversible isothermal compression of an ideal gas, and then a reversible adiabatic compression of that ideal gas to return to the original point. Now notice that energy transfer as heat in the adiabatic steps, that is zero by definition. And then we actually have energy transfer as heat in the 2 reversible isothermal steps. Okay, in this particular case, the system is expanding, and that means that you're doing work. So heat must enter the system, or energy must enter the system as heat. Right? So here you actually absorb energy as heat from a hot source of the heat engine, and you perform your reversible isothermal expansion. And here, this is a compression that is isothermal, right? So energy as heat must leave the system to be able to do that compression isothermally. Okay, now work is being done in all 4 steps, right? Here you have work being done by the system and the surroundings. This is an expansion, another expansion, so work is being done on the surroundings. This is a compression, so the surroundings are doing work on the system, and there is another compression. The surroundings continue to do work on the system. Okay, so from these concepts, we're now ready to define what the efficiency of that heat engine is. Okay, and the definition is as follows. The efficiency, which is denoted with the letter epsilon, is equal to the work performed divided over the heat absorbed. Okay. Right, so it turns out that, notice that you're only absorbing heat in this first step, right? That's when you have a hot source, and that's the only place where energy enters the system as heat. Okay, so that is going to be fairly straightforward. That is simply going to be equal to Q hot. Okay, the heat absorbed in the hot isotherm right there. And then work is performed in all 4 steps of that expansion, right? So we actually have to add up then the work of the 4 steps in the cycle to be able to compute the overall work that is being performed by the system. Now notice that we always have a sign challenge here, because we recognize that work can be negative if you're actually, the system is performing work on the surroundings, or positive if it's the surroundings that do it on the system. So to avoid that sign issues, we're actually simply going to write here the absolute value of the total work. Okay, and this is for the 4 steps. So we can actually write that this is just the work in the entire cycle. All right, so let's then see how the work in the cycle is. All right, so instead of actually calculating explicitly the work in each one of the 4 steps, we're going to be using a trick that is quite useful. Remember that the internal energy does not change in the cycle. The internal energy is also a state function, so when you go around the cycle, delta U is equal to 0. Okay, so we know that for a cycle. Well, if that's the case, then what happens is that the work that you do in the cycle, right, in absolute value, has to be equal to the heat in the cycle, and this is just simply the application of the first law to that cycle. Now the cycle only actually transfers energy as heat in either this step or that step, which we call Q hot or Q cold, right? So that would be the reversible isothermal expansion, Q hot, and then the reversible isothermal compression, Q cold. Right? In these 2 steps, those are adiabatic, so there's no energy transfer as heat. Okay, and that makes our life very easy, because now the expression that we actually have to deal with is just the energy efficiency is simply the sum of Q hot and Q cold divided over Q hot. Okay, which looks like a rather tractable expression for sure. All right, we can simplify it by simply saying that this is equal to 1 plus the heat transfer out of the system in the cold sink, right here, divided over the heat absorbed by the system in the hot source, right here. All right, so let's see if we can actually make it even a little easier here. And of course, we recognize that these steps are reversible, and that means that this is equal to the minus work. And we know that the work is minus nRT, natural log of the ratio of the volumes, right? So let's write that here carefully. The efficiency is equal to 1 plus nRT cold, natural log of the final volume over the initial volume, so V of V over V of A. Actually, it's for the cold one, so I will be from C to D, so the final volume here is V of D over V sub C. This is the heat in the cold sink, so that's that step. Okay, and the heat absorbed in the hot source is going to be nRT hot, and then the natural log of the final volume, V of V over the initial volume, V of A, for that isothermal reversible expansion, where energy as heat is being absorbed. Okay, great, so we clearly recognize that that cancels out. And the question is whether these volumes are related. And they are. We actually have seen in the prior video that when you look at the adiabatic steps, you can come up with the relationships between the volumes of those steps. That is what we have out there. And that is going to simplify our work dramatically. Notice that this denominator, V of V over V of A, is simply going to be V of C over V of D. Okay? Which is not quite what we have in the numerator, so cancellation can't be done. But we can actually do that by simply reverting perhaps the numerator. Okay, we can do that as V of C over V of D, and the only thing that that does is just change the sign of the logarithm, right? So what you actually have right here is simply that. Okay, and now these things cancel each other out, and we come up with an expression that is absolutely simple and also very beautiful. T cold over T hot. Okay, so that is the energy efficiency of a heat engine. And it turns out that this expression is actually entirely universal. It would apply to any cycle in a heat engine. It doesn't have to be exactly with these same steps. It turns out that you always get to this universal expression. So what do we learn from this? It turns out that you actually never have 100% efficiency, right? If you have a cold sink and a hot source, right, this ratio is going to be between 0 and 1, and what that means is that your efficiency is never going to be 100%, it's always going to be less than that, okay? Again, this expression does not depend on the gas that you have or any construction. Actually, you can construct the system in whichever way you want, and this will be the maximum efficiency that you could actually ever get. If your construction is not very good, then you will never reach this limit. But if the design of your engine was perfect, this will be the highest efficiency that you could ever get. Okay, so in this video we have seen how we can estimate or determine the upper efficiency for a heat engine by involving thermodynamic concepts in a Carnot cycle.